Welcome to IT.Solution, your total network, system, firewall, and security partner.
Hey everyone, and welcome to this explainer. Today, we're unpacking one of those hidden, absolutely essential protocols that literally keeps the internet from collapsing on itself. If you've ever wondered how modern networks handle redundant backup connections without completely breaking down, well, you're in the right place. We're focusing entirely on spanning tree protocol concepts today. Let's get started. All right, let's just dive right into a massive paradox. Building backup links to make a network more reliable, it can actually cause the whole thing to instantly crash. I know, it sounds crazy. Network design absolutely demands redundancy, right? We want multiple paths so that if a cable gets cut or a switch completely fails, the network just stays up. But in a layer 2 Ethernet environment, adding that physical backup loop without some kind of management protocol is a recipe for absolute disaster. So why does this disaster even happen? Well, think of a layer 2 loop like cars stuck in a giant roundabout that they literally can't exit. At layer 3, an IPv4 packet has a built-in time to live, or TTL mechanism, and IPv6 has a hop limit. When those counters hit 0, the router just drops the packet. Easy. But layer 2 Ethernet, it lacks this mechanism entirely. If a broadcast, multicast, or an unknown unicast frame gets sent into a loop topology, it doesn't expire. It just circles endlessly. It's honestly like a runaway chain reaction. When a broadcast frame hits these interconnected switches, every single switch forwards it out of every port except the one it arrived on. This causes the frames to multiply and loop infinitely. Meanwhile, the switch's MAC address table is constantly trying to update with incorrect information because it keeps receiving the exact same frame from different directions. This MAC database instability causes devastating CPU spikes and brings the entire network to a grinding halt in a matter of seconds. So here's our roadmap for today. We're going to cover the danger of redundancy, how spanning tree comes to the rescue, the inner workings of the algorithm, port roles and states, and finally, the evolution to rapid STP. Let's kick things off with Section 1, the danger of redundancy and why backups break things. The major takeaway here is that without management, a host gets caught in a literal storm of data. When a loop occurs, the link becomes completely saturated, creating what we call a broadcast storm. The switches become so overwhelmed trying to process the endlessly looping frames and constantly updating their MAC address tables that they can't even forward legitimate user traffic anymore. Without intervention, your incredibly expensive network hardware becomes completely useless. Which brings us to Section 2, spanning tree to the rescue, blocking to save the network. Thankfully, there's a hero in this story. The Spanning Tree Protocol, or STP, intentionally places a specific port in a blocking state to break the physical loop, all while maintaining a logical backup. The physical cable is actually still plugged in, but STP has effectively disabled that port from forwarding user data frames. This creates a loop-free topology where each switch has only a single logical path to reach any destination, just like the branches on a tree. And the best part? If the primary link fails, STP dynamically unblocks this backup port so traffic can keep flowing. And we literally have Radia Perlman to thank for this brilliant invention. She developed the spanning tree algorithm back in 1985 while working at Digital Equipment Corporation. She even published a famous poem called Algorum to describe how the algorithm creates this loop-free tree. I just love that. It brings a wonderful human creativity to a deeply, deeply mathematical networking concept. Let's look under the hood in Section 3, how the algorithm works through a 4-step election. The algorithm is incredibly methodical. It operates in 4 clear sequential steps to ensure a completely loop-free topology. First, the network elects a supreme leader, called the root bridge. Then, every other switch finds its absolute best path to that leader. Next, they figure out which switch is in charge of forwarding traffic onto each individual network segment. And finally, any port that isn't selected for one of these active forwarding roles, it's shut down or placed into an alternate blocking state. Think of this first step like a political election. The switches are campaigning using special messages called BPDUs, or Bridge Protocol Data Units. The switch with the lowest bridge ID gets crowned the root bridge. Now, the bridge ID is just made up of a priority value and the switch's MAC address. By default, that priority is set to 32,768. But if an administrator lowers a switch's priority, say down to 24,577, it automatically wins the election, becoming the central reference point for the entire network. Okay, so once that route is elected, every other switch has to find its shortest path to the leader by calculating what's called the route path cost. When a switch receives a BPDU, it adds the cost of the port it received the message on. So it's basically mapping out all available paths to the root bridge, adding up the costs of the links along those paths, and the path with the absolute lowest total cost becomes its primary route. It's like your GPS finding the fastest route home. Let's move on to Section 4, port roles and states, deciding what's forwarding and what's blocking. So here is where we map out the results of our algorithm. First, every working port on the root bridge becomes a designated port, meaning it forwards traffic. For all the other switches, their absolute best path to the root bridge becomes their root port. Finally, if there is a redundant link left over that would cause a loop, that port is assigned the role of alternate port, and it gets placed squarely in a blocking state. But here's the catch. Transitioning these ports requires incredible care. A port doesn't just instantly flip on. It moves through these careful, transitory states to prevent accidental, temporary data loops. Think about it. If a blocking port just immediately jumped to forwarding data, it could flood the network before the other switches even had time to update their topologies. So STP essentially forces the port to pause. It transitions through listening and learning states before it is finally allowed to forward actual user data frames. Tracing that actual flow, there are these built-in 15-second forward delay timers. When a link comes up, the port starts in blocking. Then it goes into listening for 15 seconds, where it receives and sends BPDUs, but strictly blocks user data. Then it spends another 15 seconds in the learning state. It still blocks user data here, but it actually begins updating its MAC address table. Only after that full 30-second wait does it finally enter the forwarding state. 30 seconds. In networking time, that's practically an eternity. Which leads us perfectly into our final section, Part 5, the evolution to rapid STP, speeding up the tree. You know, waiting 30 to 50 seconds for convergence was totally fine back in the 1990s. But as networks got faster, waiting that long just wasn't good enough anymore. Enter rapid STP, or IEEE 802.1. It massively speeds up the process. It's backwards compatible, but way more efficient. Rapid STP simplifies the port states by combining the old disabled, blocking, and listening states into a single discarding state. But the real magic? It allows alternate backup ports to transition to a forwarding state almost immediately when a primary link fails, completely bypassing those lengthy 15-second delay timers. We also have to highlight a real game changer, Cisco's PVST Plus, or Per VLAN Spanning Tree Plus. This adds incredible efficiency by running a unique spanning tree instance for every single VLAN. Why does this matter? Well, if you're paying for redundant links, you don't want half of them just sitting there blocking traffic all day, right? With PVST Plus, you can make switch 1 the root bridge for VLAN 10 and switch 2 the root bridge for VLAN 20. This lets you safely load balance your traffic across all your physical links while keeping the whole topology completely loop-free. It's brilliant. To wrap up this explainer, I want to leave you with kind of a provocative thought. Layer 3 routing, as we discussed earlier with that TTL mechanism, naturally allows for redundant paths and loops without having to block any ports at all. As modern network designs push Layer 3 routing further and further down the hierarchy, literally all the way to the access layer, is the spanning tree protocol destined to become a thing of the past? It's a fascinating evolution to watch. Thank you so much for joining me on this explainer. Keep your networks loop-free and keep learning.
Thank you for watching. See you in the next episode.